Hello, everybody. Mr. Hennon here, and I am going to go through the notes for fluid statics here. I realized that I hadn't actually gotten that posted, and so I just want to make sure I get through those notes so everybody's got them and we're good to go. So, with that in mind, let's move to the next one. So, this particular set of notes, we're talking about density and Archimedes principle. Those are the two major things that we're going to be tackling. Let's see if I can get a nice pin here. There we go. We'll go with white. So, the official definition of density is just that it's mass divided by volume. And our typical unit, our variable here in physics is actually going to be the Greek letter rho. So it looks kind of funny. It kind of looks like a P over here, but this is going to be our first equation. So mass over volume. Everybody's familiar with that, but we should be pretty good. I sometimes get a little more flourish to my rho, so you'll see me probably write this equation kind of like this. So if you ever see this funny, almost looks like writing a big E that kind of squiggles down or extra little tidbit to it. The other one that's going to really throw you off is the unit. Since we here in physics like kilograms and we like cubic meters, our unit for mass over volume or density is going to be the kilogram per cubic meter. Not what you typically think of. Because if I ask most people, hey, what's the density of water? You probably learned in a chemistry class that it was 1, and you are thinking grams per cubic centimeter. But we want to convert that. We want to change that over. So I'm going to go through how we would go about changing that. So the first step is if I change my grams into kilograms, we know there are 1,000 grams in 1 kilogram. So I would divide by 1,000. So it makes sense, if we're going from grams to kilograms, that it should be a smaller number. So you go, oh, it's going to be 0.001 kilograms per cubic meter. But we're not done. We haven't actually changed our cubic centimeters here. Move myself up here. So the other part of this is we have to change our centimeters into meters, but we're actually going to do a cube. So the first step, and this is kind of an interesting one, there are 100 centimeters in 1 meter. I would actually say there's 1/100th of a meter in a centimeter, but that gives us the same thing. That just does one of our cubic centimeters. So we've got to change all of them. And you can't just put cube, hey, I'll just cube the units. That doesn't work. We have to cube that conversion factor as well. So we would have to cube this 100 and cube this 1. Well, the 1 is pretty easy because it doesn't actually change anything. 1 cubed is just 1. But 100 cubed is going to be 1, 2, 3, 4, 5, 6, lovely little zeros. So it's actually a million. So there are 1 million cubic centimeters in a cubic meter. So therefore, if we cancel some of this 1,000 will get rid of 3 of those zeros, and we're left with 1,000. So the density of water we are going to use is there is 1,000 kilograms per cubic meter. So that's the density of water. Quite a big number, because if you think about it, if you had a cubic meter of water, it would have a mass of 1,000 kilograms. In terms of weight, that would mean it would weigh about 2,200 pounds, so over a ton. So just think about 1 meter by 1 meter by 1 meter, how much that would be and how crazy heavy that would be. It gives you an idea if you've ever tried to move. The example I usually give, if you have one of those little kiddie pools in the backyard and you fill it with water and then you try to move it in some fashion, it's amazing how heavy it is, and you don't even feel like you've put very much water in it. I think it also boils down that if you have like a gallon jug and you fill it with water, that it weighs about 8 pounds. So just kind of a relationship there. So let's keep going. See what we can get. So I just put this on here, just give us some common examples. Now, we're not really going to just deal with fluids. We'll also talk about solids as well, but mostly we're talking about fluids in this particular unit. So we're concerned about our liquids here and our gases. That's what a fluid is, liquid or a gas, pretty much any kind of matter that isn't a solid. But we also do bring in the solids because a lot of those numbers are familiar to us. So we've got a whole bunch of possibilities here. Pretty much all you're doing is just multiplying by 1,000 what you used to know. So if you are familiar, say, with the density of aluminum, and chemistry class, it was 2.7 grams per cubic centimeter. Now it's going to be 2,700 kilograms per cubic meter. So pretty straightforward, pretty easy to kind of convert it. We've got a whole bunch of different liquids over here that I threw in here. Water, obviously, oil being a little bit less dense, mercury being extremely dense, alcohol being less dense, and that type of stuff. And then the crazy one is when you look at these gases down here, because these numbers here are still kilograms per cubic meter. So you're not suddenly switching back to grams per cubic centimeter. So the density of air, for example, that 1.29, that's like our grams per cubic centimeter number. It's like a little over 1, but that's 1.29 kilograms per cubic meter. So if you had a container that had 1 cubic meter of air, it would only have a mass of 1.29 kilograms. That means it would weigh somewhere about 2.5 pounds. So you need a huge amount. So it's kind of a really crazy change, and it makes you realize why we can't actually float in air very easily, because we just can't get our volume, our mass down that small. Okay, let's try a little example here. Let's say the body of a person whose weight is 690 newtons contains 5.2 times 10 to the minus 3 cubic meters of blood. We want to know what's the blood's mass, what's the blood's weight, and what percentage of the body weight does the blood make up. So there's our little sample problem. My suggestion would be to pause it at this point and give this a try so you can kind of see if you can do it as well. I'm just going to kind of keep pushing through. The key thing that we're going to be dealing with on this one is we need the density equation, mass divided by volume. However, we're going to change this. We're not going to actually be solving for density. We're going to be solving for mass. So I multiply by volume, so you end up with density multiplied by volume. So that's going to be a key one. We're dealing with blood here, so we're going to need the density of blood. So we're going to come back to this slide. The density of blood is 1,060 kilograms per cubic meter. So I'm going to go ahead and put in the density of blood is 1,060 kilograms per cubic meter. And then the last one is we have weight popping in here. Weight. And I just kind of make the assumption that you've gone through physics 1, you know this equation, we know this concept, we should be pretty good. So just a reminder that weight is how much gravity is applying a force on an object. So my silly way of remembering this is you take mass times, here on Earth, 9.8. Because I use 9.8 meters per second squared for our acceleration of gravity. So the weight of an object is mass times gravity, or mg. So we usually use a lowercase w. I like to use a lowercase w. The neat thing is we can also take this equation right here and we can substitute in for mass. So you're going to see another weight equation. We'll eventually put all these on the equation wall, so we should be good, that it could be the density of a object times the volume times gravity. So I think it's kind of neat. It almost forms a nice little symmetry. That's why I draw my rows that way. So with this one, we should be able to figure out the mass, and then from the mass, we're just going to calculate the weight by multiplying by 9.8, and then we're just going to do a ratio. So like I said, if you wanted to pause, you should be good and figure it out. Boom. But if we let it go, we've got this answer. We're going to take the volume of it, multiply by the density. We get that the blood has a mass of 5.5 kilograms. We find its weight. We multiply by 9.8 and find out that it weighs 54 newtons. 54 newtons means that it's going to weigh somewhere about 10 pounds, a little over that, maybe 12 pounds. And then finally, this percentage, we take 54 over 690, and we find out that this person is 7.8% blood. So just a nice little problem dealing with density. Our next idea is Archimedes Principle. And I'm going to throw a video on here as well, that there's a couple of stories with Archimedes. So the common story with Archimedes is that the King Hero, came to Archimedes, and he had given gold to the goldsmith and said that he wanted a crown made. And so he gave this pile of gold to the goldsmith and said, make me a crown. And the goldsmith went off and pounded it in and did whatever he needs to do. And he came back and he gave him this absolutely beautiful crown. Probably added jewels and other stuff as well. But maybe it just was gold. That was kind of the idea. However, the king just didn't trust the goldsmith for one reason or another. And so he went to Archimedes. Archimedes being one of those great Greek philosophers at the time, we would say scientist now, but pretty much just a philosopher. And he said, okay, did he actually use all my gold, or did he trick me? Is he stealing some of it? How do you figure that out? So you can't really say, okay, let's see if this crown weighs the same as gold, or anything like that. But you can think of it in terms of density. So if it's made out of gold, gold has a certain density. It has a certain mass or weight for a particular volume of it. So you can easily find that for pure gold. You can take a pure gold coin, put it on a scale, find its mass. You can calculate the volume of it, and you've got it. The crown, though, is difficult. We can find its mass. We can put it on a scale, find its mass. We're good to go. But then when you take it off, unless you melt it down, you can't actually put it into an easy shape to find its volume. So how does one do this? So the assumption, or the kind of the story, is that Archimedes was in the bathhouse, and he sat down in the water of the bath, and it was so full that some of the water spilled out. And so he thought to himself, I think that an object will displace its volume equal to the volume of that fluid that is actually going to come out. So in other words, he talks about water displacement. So one of the ideas is that Archimedes came up with the concept of water displacement. And so supposedly the story goes, he hopped out of the bath, he went streaking through the streets saying, Eureka, I've found it. And he figured out a way to find the volume of the crown. He could put it into a tub of water, measure the volume of water that comes out, and then that would be the volume of the crown. He's got the mass of it, he's got the volume, he can compare it to gold. And supposedly the story is the king was correct, that the person had actually stole some of the gold, and the crown was not pure gold. So that's kind of where the story goes. However, Archimedes' principle doesn't actually stop there. Archimedes' principle isn't just the measurement of volume with water displacement. It also is this idea of a buoyant force. So if you put something into a fluid, it displaces that fluid. Well, if you can actually figure out the weight of that displaced fluid, in other words, how much fluid did it actually displace and how much does it weigh, that will actually equal the buoyant force, how much the fluid is pushing up on that particular material. So the key idea we're actually going to use is this one, that the magnitude of the buoyant force is equal to the weight of the fluid that is displaced. So this is the equation we typically have right here. I'm going to extend it a little bit because the way we're going to find our weight of displaced fluid is we'll take the density of the fluid, we'll multiply by the volume of the displaced fluid, and then we'll multiply that by gravity. So we'll get those three things together. That'll figure out the weight of the displaced fluid. That'll be equal to the buoyant force. So the idea, if I put something in water, say this cube, for example, it's going to have a certain weight. So this is the weight of the cube. Maybe it weighs 100 newtons, but there's going to be a buoyant force acting on it. So FB is how much it's acting on it. In this particular case, it would just be the weight of that much water, because that's how much was being displaced. If it floats, what we often say is that the buoyant force actually equals the weight of the object. So maybe you put this in the water, like we did with our little PhET simulation, and it floats in the water. Then all of this water that has been displaced is creating enough of a buoyant force to support the weight. So we go back to Newton's laws. We have balanced forces acting on this. This is not accelerating downward. It's not accelerating upward. It's in equilibrium. So that's the other parts when we talk about something floating. We don't have to do it in terms of density. We can also do it in terms of buoyancy. So this is my final problem here. We're going to try this raft situation. So the raft is made out of solid yellow pine wood. So it has a density of 550 kilograms per cubic meter. The raft has dimensions of 4 times 4 times 0.3. So those are the dimensions over here. Here, move myself out of the way here. So it's 4 by 4, 4, whoops, I didn't mean to go forward. I'll come back here. So 4 by 4 by 0.3 is the whole thing. And so we will have two questions. We want to know, does it float? And if it does float, how much of the raft is actually beneath the surface? So we're trying to find this little H here, if it does float, and then also the question, does it float? And we're floating it in water. So one easy way to answer this is to just do it off of density. Since the raft is made out of pine wood, which is 550 kilograms per cubic meter, and water is 1,000, that's what 1 times 10 to the 3 is going to give us. Since it's less dense, it should float. So does it float? We should say yes. That's the easy answer. Oops. The other way to think of this is, does the buoyant force equal the weight of the raft? So we can find the weight of the raft pretty easily. We can, I'm just going to jump to this page. We can take over here the volume of the raft, which is 4.8 meters, multiply it by the density of the raft, which would be 550, and then multiply by gravity, which would be 9.8. And that would give me the weight of the raft. So here's another neat thing. So if you notice on this slide, is I'm finding the maximum buoyant force. The maximum buoyant force is the 1,000 times that 4.8 times 9.8. So if the whole thing was in the water, all of the raft was in the water, it would have a buoyant force of 47,000 newtons. But I should probably flip these around. If we find the weight of the weight of the raft is only 26,000 newtons. So since 26,000 newtons is smaller than 47,000 newtons, it means that the buoyant force, the maximum buoyant force, is actually larger than the weight of the raft, and therefore it floats. So, ta-da, that's another way to do it. One of the things you'll notice is when I'm setting these two equal to each other, really what we're doing is the same idea. This was density of the raft times the volume of the raft times gravity. And then over here I had the density of the water, the volume of the water times gravity. Gravities can actually cancel, and the volume of the raft can actually cancel. And so all we're doing is we're saying the density of the raft is smaller than the density of water, therefore it floats. So we're kind of getting the same idea. Here's the next idea. If it's floating, how much of it is actually in the water itself? So actually, I'm going to go back. At any point here, you can always pause this if you want to try this out, if you want to actually try to solve this information all the way back here. And this is kind of the main idea, is we're looking at buoyant force equaling the weight of the raft. So pause if you want to. Okay, so if it's floating, then the weight of the raft should equal the buoyant force, and that's that 26,000 newtons. But over here, we can find the buoyant force by the density of the water times the volume. This is our displaced water. So in this particular case, the density or the volume of the displaced water is not going to be the 4 times 4 times 0.3. Instead, it's just going to be the 4 times 4 times the h here. So these two dimensions are there, and then we have a little h, and then multiply by gravity. And then the idea is we're going to solve for h. So that's exactly what was done here. Boom, 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 and they get 0.16, or 0.17, sorry, 0.17 meters. That's one way to do it. It's actually the long way, and it shows everything, and we're good. But I want to kind of point out a couple of things that I think are very important, and then I'll basically be done. If I go back to how I found the density or the weight of the raft, so this weight of the raft was the density of the raft times the volume of the entire raft times gravity, and we're going to set it equal to the buoyant force. So that's going to be the density of the water. I'll just put W here, the volume of the displaced water times gravity. So here's the first thing I think is kind of neat. If you notice on the left side, we're multiplying by gravity, and on the right side, we're multiplying by gravity. That means you can actually cancel out gravity. This is a crazy idea. What that means is when something is floating in water, for example, or in any fluid, actually, the acceleration of gravity is irrelevant. So I always do this silly little problem on some of my tests and quizzes. Let's say that someday they build a moon base, and you can go to the moon base and go swimming. Okay. So your first thought is gravity is like 1/6 on the moon that what it is here on Earth. You should be able to kind of float almost on the top of the water. That'll be awesome. That'll be so much fun. But what this equation tells us is if you were actually on the moon base, so basically in some kind of giant dome that still going to be air pressured so you can actually breathe, and you're just swimming, the acceleration of gravity is not going to affect how you float. You will float in that water exactly the same as if you were here on Earth. So if you sink here on Earth in most pools, you would sink there as well. So the acceleration of gravity is not going to save you from that. So it's kind of a downer, but just kind of an interesting idea with using the concept of density and Archimedes principle here. Here's the next part. When I found the volume of the raft, it was 4 times 4 times 0.3. But over here, I have the density of the water, and then the volume of the displaced fluid was 4 times 4 times h. Hey, look at that. That means that 4 times 4 can also cancel. And then I'm going to bring this over the other side. So the ratio of the densities, and then if I bring this 0.3 over, is actually equal to the ratio of the depths. So, and it's reverse. So the density of the raft divided by the density of the water should equal the amount that's in the water divided by the full height of this raft. And in other words, this is kind of like 550 over 1,000. So that's like 55%. That means that 55% of this raft should be in the water. So looking at the ratio of densities, you can kind of figure out how much should be in it. Obviously, if you end up with something that's over 100%, it means it sinks. That's pretty much all you have. That right there, ladies and gentlemen, is density and Archimedes principle. I hope you enjoyed.